Hello, in this video we're going to be starting Unit 2, which is about the derivative, and we're finally going to get to define what the derivative function is, and we're going to learn how to graph this derivative function, as well as identify where a function has no derivative. So here we are given the definition of the derivative, which says the derivative of f at a real number c has been defined as the real number f prime of c equal to the limit as x goes to c of f of x minus f of c all over x minus c, provided the limit exists. What this is saying is we can take any function here and call it f of x. So let's just draw a parabola like this and say that this is our f of x function. The derivative is going to be a number, and this number is defined by the slope as our x is approaching some c value. So we can take a value here, c, and of course its y value is f of c, and basically the derivative is that slope as we take some other x value on the function, which in turn would be have a y value of f of x there. We can take this secant line. Let me draw a better line here. That's the secant line, but as this x is getting closer and closer to c, as in approaching c, that point is going to get closer and closer and closer and closer and closer to that c value, so that once that gets closer, the secant lines are also getting closer and closer and closer to eventually get to this c and create the tangent line that we're looking for. So the derivative is the slope of this line here. And slope, as we know, is a real number. Therefore, this right here, f prime of c, is a number which represents the slope at that tangent line. So that was the definition, which we can call using form 1, which is used to find the derivative at some number c, or some x value c right there. However, we also have another form, which you can see right here, that we can use to find the derivative at any point, not just some c, but for any real number of that function. So what we can do is let that x value become c plus h. So that x value that we had here, that's just going to become c plus h, which means h represents that distance from c to that new point, c plus h. And when we do that, it's going to change our slope function here to be f of c plus h minus f of c all over c plus h minus c. And when you simplify it, those c's are going to cancel, and we're left with this function here. And because c plus h is this x here, as it's getting closer and closer to the c value here, this h has to become 0. Because then, once h is 0, we really just have c plus 0, which is c. And so then that would become the tangent line at just c. So that's why when we want to find the derivative, we have to take the limit as h goes to 0. So that way we are finding the derivative at this point c. So we have our two definitions of finding the derivative. And this is what it comes down to. When this is true, if the limit exists, then we can say the function is differentiable. In words, this form 3 says the derivative is the limit of a difference quotient. And remember, this part right here is what we call the difference quotient, and so we're just taking the limit of the difference quotient. We have a little note here. The instruction differentiate f means to find the derivative of f. So anytime you see this word differentiate, it's just an instruction to you telling you to find the derivative of f. And we're going to see a little bit of both of those kinds of directions here. So first, it says, find the derivative of the function f of x is equal to x squared minus 5x at any real number c using form 2. So form 2, f prime at the point c is equal to the limit as h goes to 0 of f of c plus h minus f of c all over h. So what I'm going to do now is go ahead and plug in c plus h to our function f of x, like that. So that's our f of c plus h, minus f of c, so that means I'm going to plug in c to that function here. Don't forget these parentheses because that negative is going to have to distribute. And this is all divided by h. So we have to simplify this a little. C plus h, we're going to go ahead and distribute this. So multiply all the way through. That's going to give us c squared plus 2ch plus h squared. I'm going to go ahead and plug that in here. I'm going to distribute this negative 5. That's going to give me negative 5c minus 5h. And then I'm going to distribute that negative 1. And all divided by h. From here, we're going to see what are some of the things that are going to cancel. So I'm just canceling out those things. And we're going to simplify 2ch plus h squared minus 5h over h. I see that they all have an h in common, so I can go ahead and factor out that h and cancel it out, leaving us with the limit as h goes to 0, 2c plus h minus 5. Direct substitution tells us 2c plus 0 minus 5 becomes 2c minus 5. So that is our derivative function for all values of c. So f prime of c is equal to 2c minus 5. And remember, c is just some x value there. So we can plug in any x value into this function here, and it's going to give us the derivative or the slope of the tangent line at any of those specific x values. Moving on to the next problem, it says differentiate f of x equal to the square root of x and determine the domain of f prime. So we're going to go ahead and use the third form that we saw here, which is the definition of the derivative as the limit as h goes to 0 of f of x plus h minus f of x all over h. So very similar to the last problem that we did, we're going to plug in x plus h into our f. So that's going to become the square root of x plus h. And then subtract f of x, which is just the square root of x, all over h. From here, we can't really do too much simplifying. If I try and do a direct substitution, we have an h in our denominator, which would mean we have a 0 in the denominator. which is undefined. So we have to use some of our limit methods at this point. We see here that these are radicals here. So I'm going to go ahead and rationalize this function. So I can see here that that's a minus, so the conjugate is going to be square root of x plus h plus square root of x. Whatever you do to the top, you have to do to the bottom. So all I did was change that sign in between the two terms. The opposite of negative becomes positive, and then everything else stays the same. So from here, when we multiply across, this times that is just going to be x plus h. Let me change this back to green. So we have the limit as h goes to 0 of x plus h. Negative times a positive will make this negative. And then root x times root x, that's going to become just a positive x. All over h, which we already had, times this new conjugate that we're multiplying by here. And that's in our denominator there. So what we can do from here is just try and simplify things. I see that this positive x and that negative x is going to cancel. And so I'm left with the limit as h goes to 0 of h all over h times root x plus h plus root x. This is all in the denominator. Those h's are going to cancel out. And so I get the limit as h goes to 0 of 1 over root x plus h plus root x. Now we can do direct substitution. When we do that, we're going to get 1 over root x plus root x. Sorry, technically that's root x plus 0 because of that h that we're plugging into, which will just be 2 root x, because root x plus root x is 2 root x. And that is going to be our derivative. So we have differentiated f, and we found that the derivative is 1 over 2 root x. And now we want to determine the domain. So we have two things that we need to think about. One is that square root, which we know can't be negative, but could equal 0. However, because it's in the denominator, overall we know that denominator can't be 0, so we cannot let that x be 0 or anything less than 0. So x has to be greater than 0 for our domain. And let me rewrite that. Domain is x greater than 0, or we can write it in interval notation as 0, can't equal 0, to infinity. And that would be our solution for this problem here. Next problem, we want to find the derivative if f of x is equal to x cubed minus 1. Then we want to graph y equal to f of x and y equal to f prime of x on the same set of coordinate axes. So let's go ahead and start by finding the derivative. So we have f prime of x is what we're trying to find. And we're going to do that by taking the limit as h goes to 0 of f of x plus h minus f of x all over h. So our function is x cubed, so this is going to become x plus h cubed minus 1. And my f of x is going to be that same function, all in parentheses, and all divided by h. So again, lost my page here. There we go. So again, we're going to FOIL this out. The limit as h goes to 0. X plus h cubed is equal to x cubed plus 3hx squared plus 3h squared x plus h squared. We still have that minus 1 hanging out there, so I'm going to put a minus 1. And then I'm going to distribute this minus here. So that gives us minus x cubed plus 1. All divided by h. And now that everything is FOILed out, I'm going to look and see what is going to cancel. And those are opposites. So now I'm left with the limit as h goes to 0 of 3hx squared plus 3h squared x plus h squared over h. I can factor out an h from each of these terms. So that leaves me with 3x squared plus 3hx plus h over h. Cancel out those h's, and we get the limit as h goes to 0 of 3x squared plus 3hx plus h. Oh, and we canceled out the h, so we don't even have an h there. Okay, from here, we're going to do direct substitution. So I'm going to plug in 0 for these two h's that I have. That's going to leave me with 3x squared plus 3 times 0x plus 0, which is just going to become 3x squared. And that is our derivative. Next, it asks us to graph y equal to f of x and y equal to f prime of x on the same set of coordinate axes. So I'm going to scroll on to the next page here where I have the graphs already. We're going to go over how to graph these. So, first of all, we have this function x cubed minus 1. So we should be familiar with the parent function here of x cubed, and it's just shifted down 1. That's what that minus 1 is telling us. So it's just the x cubed function shifted down 1. And now we have here the parabola 3x squared, and we just have a dilation here. We're multiplying it by 3, so it's getting just a little bit wider here. And now we're going to take a look at how we can go from this original f of x to this derivative function. So we want to start out by looking at some of these points. You can kind of pick out some random points, but we can see from the picture there's some points that are going to be pretty important, especially right here. So at 0, negative 1, that's the point right here, the slope is equal to 0. So if I come down to my derivative function, this right here, this is the point that comes from that. So the y value of this derivative function is actually the slope at that x value. And remember, our slope here is a horizontal line, and so a horizontal line has a slope of 0. Now for the other ones, we're going to kind of have to guess a little bit. Let's see, when x is equal to 2 is right there at that point. So if I draw a tangent line, I can kind of start to estimate what the slope of that line might be. And so from the looks of it, we're going to say the slope is equal to 12. We see that it's an upward slope, so we know it has to be positive slope. And it's pretty tilted up, so we're going to say it has a slope of 12. So now in our derivative function, we see that the x value is 2, and then here the y value is 12, which was our slope. when x is equal to 2. So all the way through, we can start to kind of picture some of these slopes. Again, this one has a positive slope. It's not as inclined as the other one was. It's a little less slanted upwards, so the slope is a little bit smaller here. We estimate slope to be equal to 3. So for our derivative function, we can see that when x is -1, the slope is 3, and that's the y value here of the function. Same thing here. We can estimate this to have a slope of 12. So then when x is -2, our slope is 12, and it creates this point on the derivative function. So all of these points, the y values of these points, represent the slopes at those points here. And together, they all create this shape, which we call the derivative function, and which we can figure out algebraically from this method that we have up here. So 3x squared is that shape that is created once we take the y values, or the slopes here, and create them into y values down here. We have another example here. It says to use the graph of the function y equal to f of x, shown in figure 12, to sketch the graph of the derivative y equal to f prime of x. So we're going to do the similar thing that we did in the other problem. I'm going to pick these points here. So I have this point here that I want to find the slope of. This point here, find the slope there. Another one here, we want to find the slope there. And then another one here, we will need to find the slope. And another one, we need to find the slope of that tangent line. And we're going to try to match them up as best as we can onto our coordinate plane here. So I'm going to set this up. We have 1, 2, 3, 4, 5. We'll leave it at that for now. And then 1, 2, 3, 4, 5. All negatives. And then we have our y values, which will go up to 1, 2, 3, 4, 5, 6. We'll go up to 6. And we'll go down 1, 2, 3, 4. We'll just go up to there for now. Okay, so let's start out with this point here. -4, -3. We see that it's a positive slope because it's going upwards. And the line is rather steep. So we're going to estimate the slope to be close to 6. We'll just say m is equal to 6. And you can try to check the rise over run and see what kind of estimate you can get there. We're going to say m is equal to 6. And we're going to go ahead then and plot the point -4, +6 right there, because that represents the x value and its matching slope that we find there. Next, we're going to try to find the slope here. We see that this is just a horizontal line, so when x is equal to -2, I'm going to say the slope is equal to 0. So that means we're going to have the point -2, 0 right here. And continuing here, we have the point 0, 0. And we see that it's going downwards, so it's going to be a negative slope. And I'm going to go ahead and estimate this to be a slope of -2. So that means we're going to have the point 0, -2 right here because that was the x value of 0 and the slope was -2. Continuing to the next point, this one again has a slope of 0. So at the x value of 3/2, our slope is going to be 0. And we're going to go ahead and put that point in right here. 3/2, 0. And lastly, we have this slope right here, another positive slope. And I'm going to estimate this slope to be equal to 4. So the x value here was 3, the slope is 4, so I'm going to draw a point at 3, 4, right up here. So together, I'm going to go ahead and connect the dots to this function. And we're going to take a look at what we created here. Just by connecting each of these slopes, that is going to be the derivative of the function f of x here. So this is now the graph y is equal to f prime of x, where this was f of x here. Alright, continuing on to the next topic here, we're talking about where does the function not have a derivative. So remember here, we're picking out points and then we're just figuring out the slope at each of those points. Well, there's going to be some situations where we're not going to be able to determine the slope of the function. So take, for example, here we have what looks like the absolute value function. And right here, when f is 0, 0, we have the point there that ends in the corner. So if we wanted to find the slope here, it's pretty hard to determine the slope of that tangent line because it's coming to just a point. So since we can't determine the slope, we say this function has no derivative or is not differentiable when x is equal to 0. And you can see here that we can check this actually whenever we find the limit as x goes to that c value, in this case as x goes to 0, from the left side of this function. So I'm going to go ahead and set this up, and then maybe you can try this on your own. We're not going to go through what the limit actually is, but you would want to check the limit as x goes to 0 from the left of f of x, which is, in this case, absolute value of x, minus f of c. So if our c is 0, and I plug in 0 to that function, that's just going to give me 0. So minus 0 over x minus c, and our c again is 0. So we're finding the limit as x goes to 0 from the left of the absolute value of x over x. And we're not going to go through exactly how to solve this, but this is going to be -1. And if you do the same thing for the limit as x goes to 0 from the right of this function, it's going to be +1. And so even though they both exist, we see that they are not equal, and therefore it's not differentiable. And so whenever we have this kind of situation where the limit of this difference quotient exists from both sides, but they're not equal to each other, they're creating a corner, which we know when a function has a corner, we can't find its derivative at that point where the corner is. Next, we're going to look here. So this is the function f of x equal to cubic root of x. And if we look at the point 0, 0, if we try to determine or draw the tangent line, we see that it's a vertical line, and we can't determine the slope of a vertical line. It just doesn't exist. So therefore, if we can't determine the slope, its derivative does not exist as well, or it's undefined. And you can check the one-sided limits just like what we did here in this section of each of those, and you're going to see that they're both going to equal infinity, or they're both going to equal negative infinity. In this case, I believe they both equal infinity. For the cusp, a cusp is when the function comes together and it creates this little shape here. It's almost like those little birdies. It's kind of like a corner, but it's kind of curved coming inwards. And so at this point here, we can't really determine the slope of the tangent line. It's kind of hard because of the way the functions come in from both sides. Therefore, it's not differentiable. We can't find the derivative at that specific point there. If you take the limits, the one-sided limits of this function here, just like what we did up there, you're going to see that one side is going to equal negative infinity, and then the other side is going to equal positive infinity. And that is a sign that we have a cusp in the function. And therefore, again, the function has no derivative. So we have another example here. Given the piecewise defined function f of x equal to negative 2x squared plus 4 if x is less than 1, and x squared plus 1 if x is greater than or equal to 1, we want to determine if the derivative exists at 1, or at x equal to 1. So what we're going to do is we're going to go ahead and find the limit as x goes to 1 of the difference quotient. So we have the limit as x goes to 1 of f of x minus f of 1 over x minus 1. And we're going to investigate this limit here. So this should be 1. So we have f of x minus f of 1. Well, if we look here, when it's equal to 1, we're going to use this bottom part here. So x squared, we're going to plug into that. 1 squared plus 1 is just 2. So I'm just going to write 2 here. And then we have x minus 1 down here still. So what we're going to do next is just go ahead and investigate the left and the right hand side. So from the left side, our f of x is going to be this top part. So I'm going to plug that in for f of x here. And then we have the minus 2 all over x minus 1. So this is going to become, I did it again. There we go. The limit as x goes to 1 from the left of negative 2x squared plus 2 all over x minus 1. We can't do direct substitution just yet, so I'm going to try to simplify this or factor this. Factoring out a negative 2 leaves me with x squared minus 1 over x minus 1. That is the difference of 2 squares. So we have negative 2 times x plus 1 times x minus 1. Those x minus 1's cancel. We get the limit as x goes to 1 from the left of negative 2 times x plus 1. And direct substitution tells us our limit has to be negative 2 times 2, which is negative 4. So that is our limit from the left side. Now we can find the limit from the right side. The limit as x goes to 1 from the right, and we're going to be using this x squared plus 1 as our f of x. Minus 2 all over x minus 1. This will simplify to x squared minus 1 over x minus 1. And again, we have the difference of two squares. X plus 1 times x minus 1 all over x minus 1. Those will cancel. We get the limit as x goes to 1 from the right of x plus 1. Plug in our 1, or do the direct substitution, and we get 2 as our limit from the right side. So, our limit from the left side is negative 4. Our limit from the right side is 2. That means that this function is not continuous. They're coming in from two different sides, and therefore our limit does not exist. Our general limit, I should say, which means that f prime of 1 does not exist because we could not find the limit for this function when x approaches 1. So for this next problem, we have y equal to f of x is a function that is continuous for all real numbers. And this figure 19 here shows the derivative of that graph. So this is f prime of that function. We don't know what f of x looks like. However, we're going to look at some of the key points here to determine what is going on with the original function f of x. So, Part A asks, does the graph of f have any horizontal tangent lines? If yes, explain why and identify where it occurs. So what we need to do is think about these connections that can be made from the original function to the derivative function. So think about, where did we have horizontal tangent lines? We had one here, and we also had one right there. And how was that represented in our derivative function? So we can see here and there, it was represented by x-intercepts. So if we come over here to our function, we want to pay attention to any x-intercepts that we might have. So we have one x-intercept here at negative 2, and we have another one here at 4. So that means that our original function is going to have a horizontal tangent at x equal to negative 2 and at x equal to 4, because there are x-intercepts here on the derivative function. So yes, our function, or our graph f, has a horizontal tangent. Yes. F has 2 horizontal tangents. Tangent lines at x equal to negative 2 and at x equal to 4, because f prime of x has x-intercepts at those points. Now part B, we want to determine if the graph has any vertical tangent lines. If yes, explain why, identify where it occurs, and determine whether the point is a cusp of f. So we're going to go back to this chart here and look at what does it mean to have a vertical tangent line and what does it mean to have a cusp. So to have a vertical tangent line, we see that both sides are going to equal positive infinity, or they're going to equal negative infinity. And the key word here is both. Whereas here for the cusp, we know that there's a cusp if one side of the limit equals negative infinity and the other equals positive infinity. So if we go back to our function here, we see that when x is going to 0, or when x is equal to 0, this function has some infinite values here. We see that they're both both sides of 0 are actually going to infinity. So that means we do have a vertical tangent line when x is equal to 0, and it's not going to be a cusp because we see that they're both going to positive infinity. So yes, f has a vertical tangent line at x equal to 0 because the limit as x goes to 0 of that function is positive infinity. This point is not a cusp. We know it's not a cusp because both sides are going up to positive infinity. Part C, we want to determine if the graph has any corners, and we want to explain why. So going back to our chart here, we know that we have a corner when each of these limits exists, but when they are not equal. So let's look at the derivative function. We see one point here when x is equal to 2, and the limit from the left side of that exists. It's that point right there. The limit from the right side also exists. It's that point right there, which it looks like the left is 2, the right is 1. However, they do not meet at the same point. Therefore, we know that this graph does have a corner because those two limits are not equal to each other. So yes, f has a corner at x equal to 2 because the limit as x goes to 2 from the left of our function is not equal to the limit as x goes to 2 from the right of that function. And that completes our analysis of the derivative function to determine what is happening with our original function. So if I kind of erase all of these so we can get a good look at the graph here, we can see just from looking at the derivative, we're going to have two horizontal tangent lines. We're going to have one vertical tangent line, and we're going to have one corner. That sounds like one really fun function. If you wanted to take a minute and try and sketch out what that might look like, you can go ahead and give that a try. That could be a fun little activity. So next we have the theorem that says if a function f has a derivative at a number c, then f is continuous. So that means if we can find the derivative, then that function has to be continuous. And we then have the corollary, which says if a function is discontinuous, we cannot find the derivative, or there is no derivative at that point. So in other words, we have differentiability, which implies continuity, but continuity does not imply differentiability. So what does that mean? Let's see if these graphs here can help us understand it. If I look at this function automatically, I see that it is continuous. So if I wanted to determine if the derivative at x equal to 1 exists, I know that it exists because it is continuous. However, if I go ahead and take a look at this graph, it is a continuous function, right? There's no holes, there's no asymptotes, but if I zoom in on that point right there, we see that this is creating almost like a corner there. So if we were to try to find the slope at 0, 0, we wouldn't be able to determine what that slope is because of that corner that we have at that specific point. Therefore, our derivative at 0 does not exist. Even though it was continuous, it does not exist. So it goes back to the idea here, continuity does not imply differentiability. So just because a function is continuous doesn't mean it's differentiable. We could also have things that have corners, which are continuous but not differentiable at a point, and we have cusps that are continuous but not differentiable at a point. Here we have a graph which is obviously discontinuous here at that point 0, 0, or at 0 when x is equal to 0. So if it's discontinuous, it automatically does not have a derivative at that point. So it goes back to this idea here. Differentiability implies continuity. If the function is not continuous, or actually it kind of goes with this corollary, if the function is not continuous or it's discontinuous, then there's no derivative. Because how are we going to find the slope of something that doesn't exist? If it's discontinuous, especially if we have an asymptote, like a vertical asymptote, let's say right there, how are we supposed to find the slope at that point when there's nothing there? So, if a function f has a derivative at a number c, then we know the function has to be continuous if that derivative exists. So this last problem here says determine if the Heaviside function u of t, or u sub 0, u naught of t, is equal to 0 if ft less than 0, 1 if t is greater than 0, has a derivative at 0. So determine if this function has a derivative at 0. This right here is telling us that something is going on at 0. So I'm going to go ahead and draw out what this looks like. So t0 is right here in the center. Oops. So if t is less than 0, we have 0. So that's going to look like this. Just like that. And then if t is greater than 0, we're going to be at 1, or greater than or equal to. So it's going to be equal to 0, and it's going to be 1 that whole entire time. So this is what the function looks like. What is happening when x is equal to 0? We have a discontinuity because there's a jump discontinuity. Therefore, the derivative at 0 does not exist. The function u naught of t does not have a derivative at 0 because of the jump discontinuity. And that's it. Because it's discontinuous, we automatically know the derivative does not exist. We have one more thing I wanted to mention here before we finish up. So this is differentiability on a closed interval. So if we were trying to check if a function is defined on the closed interval from a to b, then we can easily investigate the derivative of every number c in the open interval. That's what we've been doing this whole entire time, is figuring out what is that derivative for any value of c. However, we have to handle these endpoints a little bit differently. So what we want to do is the right-hand derivative of f at a, for example, is going to be defined as the right-hand limit. So right here, the derivative at that a, that endpoint a, is going to be the limit as x goes to a from the right of a. And then if we want to check the left-hand derivative of b, then we're going to do the limit as x goes to b from the left-hand side. So that way, if these two exist, if f prime of a exists and f prime of b exists, then we know the derivative exists at every number c in the closed interval and also the endpoints. So we know the function is continuous on that closed interval as well. So whenever you are talking about closed intervals, remember you want to handle those endpoints a little bit differently and think about what is the left and right hand derivative.